Okay, so am I audible to you? Can you hear me?
Yes.
All right. So waves are of two types, and basically what waves are, they transfer energy from one point to another without the transfer of medium. So it's basically the vibration of particles that transfers energy from one point to another. And there are two types of vibrations that are basically associated with wave motion. The first one is very simple and common that we've seen in everyday life, that is the transverse wave or the transverse type of motion of particles, and the second one is longitudinal. So these are the types of motion basically that are given to the waves just by looking at their particles. That how do they move when the wave is transferring energy through them, or by this method. So the transverse wave, I would give you some examples. For example, the water waves that you see in the water surface, they are transverse, right? Waves produced the electromagnetic spectrum, in which we have infrared, gamma rays, X-rays, so on and so forth. That's a separate chapter that we have. So they are also transverse in nature. Similarly, we have wind, that is also transverse, wind energy, and tidal is basically water that comes from the seashores and so on and so forth. So that is also transverse. And longitudinal primarily is simply the sound wave, and then we have ultrasound. Then there is one more type of wave that is associated with your syllabus. Let me just show that to you on the screen. Just a moment. Let's resume from where we left. So these are the real life examples of transverse and longitudinal, but how do the particles look like? Or what does the particle motion look like? That is why we have created this distinction between the particles or the types of waves, for example. So what's happening is that while transverse wave is being generated, or when it is generated through the system, the particles of the medium may be at a rest position previously. For example, there is no wave moving through them, they are on their mean position, rest position. So as soon as a wave is generated, or a wave tries to pass energy from one point to another, and let's consider this the source where the wave is being generated, and this is where the source wants to go. So this is the ending point or the destination where the wave is actually eventually going to travel. So we can say that the energy is going to travel in this direction. The travel of energy or the travel of wave will be in this direction. So when this wave actually originates, this is how we look at that wave. And to put it into plain perspective, the particles that are in the red position, they are in the mean position previously that there was no wave. Now these particles have been displaced to new positions as the wave tries to move energy from point A to B. So basically what has happened is that as a wave tries to pass through them, the particles have been displaced from their positions to these new positions, and similarly so on and so forth. This is how they're going to go, or this is how the particle motion is going to be. So how do we discriminate between a transverse and longitudinal wave? Is that we discuss the motion of these particles in both types of waves. Now if I try to exaggerate this motion a little bit more to understand, I can consider that the motion of particles will be in this direction. This is sometimes informally, it is sometimes said as upwards and downwards motion, right? Do we see that these particles will be moving upwards and downwards from their mean position while the wave tries to transfer energy through them? Can we see that?
Mm-hmm.
Now, transverse wave, or the definition, is specifically in this way that, okay, I'm just going to write this down the other way. So it says that when particles move perpendicular to direction of propagation, propagation simply means movement or flowing or moving through one point to another. So perpendicular to the direction of propagation of wave, Now, sometimes what students do is they try to remember this or they try to memorize it, but they make one mistake. They say, then when it moves perpendicular, when they write down it, now it can be both things. It could be particles, or it could mean that you're talking about the wave. Here, I'm emphasizing this one more time. You have to specifically state that when the particles move perpendicular to the direction, not when it moves to perpendicular, right? So it just creates an ambiguity which is not good for our grading system. All right, so where do we find this perpendicular effect? Where do we find this? We find this if we closely analyze the situation. I can see that the wave is trying to move in this direction, but the direction of particles is upwards and downwards, and I can see an angle of 90 degrees forming at this place. Do we understand where the word perpendicular comes from and where we actually try to locate it? Yes, do we understand this?
Yes.
All right, all right. So this is the definition, and this is how we're expecting the particles to move. I will also show you an animation over here in this way, over here, right? So, and we will try to learn a few wave terms before we can move ahead. Okay, so the next one is a longitudinal wave. Now, since we're going to do that in sound and ultrasound once more, I will not be discussing this in detail, but just a bit of information so that we can understand how the particles move. So in longitudinal system, this is, for example, where the particles are already placed in that scenario. Now let's discuss how the sound actually moves or is produced. It consists of rarefaction and a phase of compression. So basically, we will identify this later. So basically what happens is that if there is a speaker, it could be you, it could be just simple speaker that is trying to produce a sound. What it does is it tries to move the particles forward, so it collides with the next one. This particles also move forward, it collides with the next one. So eventually from the source, after colliding with the next and the neighboring particle, they provide energy or they transmit energy to the receiving end. So when somebody is speaking, or when you or your friend or anyone in a single room there, you're talking to each other, what's happening is that the particles between you and the person's ears are moving in this way so that they carry energy from you to that point. But there's one little detail that we're missing right now, is that when the particles are actually displaced from their original position, they would want to try to come back to their original position after that pressure or after that compression phase has passed away. So after it's done with that. So for example, if this particle in some form of its life, in one part of its life cycle, had moved towards the right side, in the other instant of time or in the other life cycle, it would come back to the original position by moving towards the left. So basically the same single particle keeps bouncing between two fixed positions while it started from a mean position. This forward and backward, back and forth motion produces a longitudinal wave. And when we talk about why is it longitudinal, it's pretty evident, or it's pretty easy to remember that wherever the wave is moving or is trying to carry energy, I can observe particle motion being parallel to it. Over here, I observe it to be perpendicular. But on the other side, I see that the particles are moving in the same direction effectively, just forward and backward, but moving in the same direction as the direction of the travel of the energies, waves energy. Do we understand this point?
Yes.
So these are the two clear distinctions between a longitudinal and a transverse wave. And over here, if I had to write down the definition, when I would write down that when particles, do not write down it, when particles move parallel is a more scientific word. Students, I've seen sometimes students write down back and forth, forward and backward. Both are acceptable, but I would recommend writing down parallel. So back and forth, but over here you cannot write down up and down. I may be using these terms for the sake of discussion, but you cannot write this down in your exam. You can't do that. Do we understand this point? All right.
Yes.
Okay. So you must not write this down. Okay. So when particles, again emphasizing, move parallel, The rest of the definition is same. Move parallel to the direction of propagation of a wave, right? So this is transverse and longitudinal wave. This is the difference between them. Now let's try to figure out what are the two phases of sound wave or longitudinal wave. One is a compression phase and one is a rarefaction phase. As the name suggests, compression, particles are close together, they are tightly packed and particles are close together. And on the other hand, we have rarefaction, particles are further away from each other. Particles are away. Now how do I see that in real life? So basically what's happening is that if I draw the particles on their mean positions like this, when I say mean position, that means that this is their starting point where they existed before there was any longitudinal wave. Okay, so let's say that we observe a compression phase at this location, okay, and there is some compression of course in this location as well. So I realize that over here the particles may now exist on these new current positions as extended from these locations. I'm drawing them separately so we can visualize it. I see that they are at these locations as opposed to their previous locations. So this was their previous location and now they have moved towards this direction. I can see that in comparison to the previous motion or in comparison to the previous life cycle, I can see that the particles have clumped closer together in comparison to before. So this one would become a compression phase where the particles are close together and under high pressure. But if I observe these particles and of course these particles, they are practically moving away from some other life cycle, from some other side that is on the other side which I haven't been able to draw. So if they're moving away from that, then that would create an area of low pressure, or you can say an area where the particles will be less in number. So this would produce a rarefaction phase. Now let's try to do this with more number of particles so that we can highlight it better to properly visualize it. I will also show you a video regarding that. So over here we can see that there are some particles that would be tightly packed, close together, and some particles moving further away because they are trying to get closer to some other section. So again, some particles moving away because they're trying to get closer. So what's happening is that these particles were trying to get close together and these particles were trying to get close together to this side of the section. Similarly over here they were trying to get close and they were trying to get closer to this one. So they're trying to make a pair with the respective group of particles, and we can see that this leaves behind a space where there will be no or less particles. Do we understand this point? So this one,
Yes.
this one would be a rarefaction. Although there are always particles, when I say there will be no particle, that would mean vacuum. There is no vacuum over here, there are just less particles. So this is rarefaction and this is compression. That is how sound wave moves between two people, or of course any number of listeners and any number of sources. That is how sound is actually moving. We will get to this later when we officially start the chapter of sound. In today's lesson we are going to understand a few wave terms associated with waves so that for their discussion it becomes easier for us. So the next topic that we have is wave terminologies or wave terms. What I would recommend is looking for these definitions from the book and trying to memorize it from there. I will only be explaining what each word would mean. So the definitions that we have are amplitude, then we have time period, then we have a frequency, then we have crest, we have trough, and then we have phase. Phase is purely an A-levels topic, but I see that if I've observed in my student that if I explain it right now, they don't have a hard time understanding what phase is when they go to A levels. It's going to get very difficult when you take this up in A levels, the term phase. And we also see that in wave terms as well, in the topic of, primarily in the topic of wavelength. When we are discussing wavelengths, then this topic or this word actually shows up in the definition. And I, as a teacher, I would like to explain this a little bit more than that is required, so that it helps you to understand even when you go to A levels. Anyways, let's try to discuss all of these terms one by one on this reference animation that I've just pulled up. Can you see this? I haven't played it, but can you see this on the screen?
Yeah, I can see.
Okay,
Yeah.
so I'm going to play this on screen in front of you. Try to see if you can see how the wave is being produced. Can you see that?
Yes. So it's a transverse wave, obviously.
Yeah,
Uh.
because the particles are moving upwards and downwards,
Yeah. Yeah.
right? Now, there's one misconception about this type of wave, that the medium transfers or travels along with it. For example, if I pause it over here, sometimes the students perceive that maybe this part of the, let's say if this was a water wave, it looks like that as if the water itself is moving towards the right side. But that's not the case. If you try to elaborate it further, just focus on this green particle that you have, this green particle, right? Just a moment. Focus on this green particle that you have right now, okay? You will see that it is only moving upwards and it's only moving downwards. It's not moving forward, right? I'm going to play this again. Try to observe this point. It's not moving forward. It's only moving upwards and downwards. So this tells us, or this confirms us, that the mediums matter. The water itself or the particles themselves do not move in the direction of the energy. It looks like as if they are moving, or the water itself is moving from the source to the end, to the ending point, but the particles basically are moving upwards and downwards and transferring energy to the next particle. They themselves are not carrying energy forward. Do you understand this point? The green particle still is on its own location. Has it changed its position?
Yes.
It hasn't, right?
Understand.
Do we understand this one? Okay.
Yeah, they only move up and down, and
Yeah,
then yeah.
Yeah, all right. So I'm going to draw this along the green one, the green particle. As we can see, it is still moving upwards and downwards, and it's rejecting, or you can say it's not moving in this direction where we were expecting energy to flow. We were expecting energy to flow in this direction, but it's not. And of course, if we extend it a little bit further, we can see that it will make an angle of 90 degrees over here. That shows the perpendicular motion of particles. Do you understand this point? Right? So this is the first misconception that we have among the students, as if it looks like that the particles itself, for example, let me just draw one ball over here. It looks like that if the ball is moving with this, right? But that's not the case. The ball is moving along the wave, but the matter, the content of the water wave, the content of the water, the content of the wave is not moving from its own position. They are just vibrating upwards and downwards. They are not moving forward. Do we understand this point?
Yes.
This is one of the misconceptions that you take as a student from the real life perception. So I'm just emphasizing it more and more. You will find this in every definition, that the matter does not move, particles move, and then they transfer energy to the next particle. All right. Now let's try to pause this at this point. I'm going to pause this animation at a single instant. Okay. Now I'm going to erase this. Okay. All right. So the first term was amplitude, right? So where is this amplitude? This is amplitude. This is also amplitude. This is also amplitude, and so on and so forth. Over here, what we see is that the amplitude is reducing with time. In real life, that is how it happens. But in your case, in your syllabus, it would assume, or the examiner would try to make sure that whatever wave that you're given, it has the same amplitude across the board, so that whenever you draw a graph like this one over here, right, whatever graph that you draw, whatever amplitude that you have, it stays the same across the board. Do we understand where amplitude exists, or where it is? It is from the highest particle to the mean position. The distance from the highest particle basically is displacement. From the highest particle to the mean position, and the central point is known as the mean position. Do we understand this?
Yes.
Now,
So displacement of highest particle from the mean position.
yeah,
It's initially.
it's always going to be the particle that has the maximum displacement, the maximum displacement particle. And for this is basically a distance, but for other particles, what would you say? For example, if you had a particle that is at this location, for example, or is at this location, for example, what do we call the distance for these particles? We simply call it displacement. We don't call it amplitude. So amplitude is a special name given to that particle that has, for that given instant in time, the maximum displacement. That is it. Do we understand this point? Right?
Yeah.
So that would be amplitude, the maximum displacement. Now the next term that we have, is crest and trough. Now the crest, where do we find the crest? The crest would be, for any given cycle, the particle that is at the top. For every section, this is also a crest. This is also a crest. This is also a crest. Do we understand this point? And then we have the lowest points. The lowest points of a wave, they will be known as troughs. Is that all right?
Yes.
Okay. Similarly over here, and we also find them over here. Okay. All right. Then we have. So what have we done successfully? We've done amplitude. We have done crest. We have done trough. Now let's look at wavelengths, and then we're going to move towards time period, phase, and frequency. So what would be the wavelengths? It's very simple. Wavelengths would be between crest to crest. It will be between trough to trough, or it can be from one mean position to the next mean position, where it actually starts and stops. Do we understand this point? Yes?
Yeah.
You will find another definition for wavelengths. Let me write that down over here. I'm just going to clear this out. I'm going to write down the definition of wavelength specifically to discuss it. So it says that it is the distance between two consecutive crests or troughs, as I've just shown, or it is the distance between two particles that are in phase. Now this is a new term, phase, that are in frequency. They go hand in hand. Let's try to see what is time period. Time period is the time taken for one complete wave to pass a point. Okay, and similarly we have a frequency is the number of waves produced specifically in 1 second. You cannot write down a per second or unit time, you have to specifically write down 1 second now. This is the new addition, or you can say new improvement in the syllabus. Previously it was number of waves per unit time, number of waves per second or something like that. No, it's going to be number of waves produced in 1 second, explicitly in 1 second. Okay. And the formula for frequency is F equals to 1 over T, and T is the time period, and the unit of frequency is Hertz, that is Hertz, and it is represented as Hz, capital H and small z. Okay, so what does that mean? It means, if I come back at this point and I see, or try to realize what would that mean, it means that what is the time taken. Let's say I select this point to be my starting, and I'm looking for my wave. If I start my wave, for example, I start my stopwatch at this location. Let's say I start my stopwatch at this location, right? Then I stop it at the point when there is one complete wave that has passed through it. So what would that mean? Let's look at this. So I have started the stopwatch at a crest. I will be expecting another crest to pass this point, so that I can consider that as one complete wave. Now let's move step by step. I can see that there is another crest approaching from this side. Do you see that? I can see that there is another crest approaching from this side to this point. Is that so? Yes. So I'm still considering, I'm still counting my time step by step and waiting for this crest to reach me. Step by step, I keep waiting for it, I keep waiting for it, and at this point, when I get my crest back, the time taken for this whole process, I would say, or I would consider that to be my time period. Do you understand what has happened? One wave, or one complete wave, has actually passed from that point, or the point that I selected, right? Now let's continue this in faster motion and see what happens. Just a moment. Let's start it again. Okay, so at this location I'm going to start it again, and let's keep on measuring the time till the next peak arrives. Okay, so approximately at this point I can say I've received my peak. Okay, do you understand this point, right? So how much time has passed by while I have done that? So I can say that the time period that is 0.35 seconds. Can we say that?
Yes.
And if I had to find the frequency, what would I have to do? 1 divided by t, and I've already found the t, so that would be 1 divided by 0.35. There may be some difference in the value, reason being because we are not particularly being very accurate over here, but we should get an answer close to 3 Hertz, as I've set the frequency to be 3 Hertz. Do we understand this point? Yes. So 1 divided by 0.35, can you try that? So I'm getting 2.9 after 2 significant figures, which would be approximately 3 Hertz if I had been more accurate with my readings. Do we understand the difference between the time period and frequency?
Yes.
Any problems, any issues at this point? Front. It's very important to understand this point. What is wavefront? Let's just give me a minute. I will show you an animation. I'm sure you may have seen water dripping down this way in a bowl. Yes. And now this is the top view. Now let's move towards the side and see what it does and what it looks like. This is what it looks like from the side. Do we understand this? And the top view would be this one. Now let me highlight one point over here. What is that? I'm considering these highest points, or these crests, because the crest is the highest point. I'm considering these highest points. Just let's pause at this location. Okay, over here. So I'm considering these highest points, these ones, as my lighter bands. You can say that if I had switched to top view, you can see it over here as well. Do we see that? That these lighter regions, the blue ones, these are basically my highest points of wave, or you can say these are my crest of the waves. So if I look at it from the top, when I see these lines, these are basically all crests joined together. And when you join together all these similar crests of a single line, this would become a wave front. So do we understand what a wavefront would be?
Yeah.
Okay. Let's try to look at it from the side again. Right? Okay.
So would you just consider the direction of the propagation of the waves, like the direction in which all the crests are?
No, not in what the direction of the crests are moving per se. We're not saying that. We're just saying we know that the wave is moving outwards like this. It's moving in this direction, away from the source. We do know that. I don't understand what you're concerned about.
Okay. Never mind.
All right. Okay. So, do we understand what is a wavefront? Okay. Let's.
Yes, you could just.
Let's play this animation again to get it better visualized. Okay, so I believe that we understand how the wavefronts look like from the side and from the top. Okay, all right. This is a wavefront, by the way. We are observing it from the top. Okay, so it bounces back from the wall. Yes. Now just observe at this point. This is a wavefront coming towards a barrier that is at an angle. Okay, so let me draw a few things on here. So we have a barrier at this location. Okay, this is my wavefront that is about to collide with the barrier. Okay, so when it eventually does reach this location, notice what happens to the wavefront. So this would be my normal. When I say normal, that is basically a reference line for simple calculation or simple understanding the concept. So this would be my normal. I draw the normal where my wavefront collides with the barrier, and it has to make an angle of 90 degrees with the barrier. Of course, I am drawing multiple wavefronts at this location because I'm trying to consider the wavefront at multiple instants in time. The wavefront itself is only one. Originated is only one, right? Now, the angle of incidence would be this one. This one would be the angle of incidence. because this is how the wave was traveling towards the wall. Okay, so these, okay, so if this full wave was still available over here, okay, this is the part that has been reflected, or this is the part that is missing. I can't see that over here, and this is the part that still has to collide with the barrier. Okay, so I would consider this as my angle of incidence, and all those particles that have collided, or they would have been over here, but they are not. Why? Because they have collided with the barrier first. As I can see that this part of the wave is going to collide first, but this part of the wave is going to collide much later than that because of the distance. Do you understand this point?
Yes.
Now let's try to play this video more and see what happens. Just observe how the wave is actually, okay. Do you see that over here, how it has responded to the reflection from this barrier?
Yeah, you can see that the angle is same stuff instance, so
Exactly,
reflection,
right? And over here you can see that this is my angle of reflection, right? So the part of the wave that was missing and the part of the wave that still has to collide with the barrier are still here. They're still over there, right? So there is some part of the wave, let's divide it in two parts. A part of the wave that is, or that still has to collide with the barrier, and a part of the wave that has already collided with the barrier. So what happens to this barrier is that it actually becomes bent somehow, like this, because of the reflection. It becomes bent, just the way that we can see in this location, right? And the rest of the part that still has to collide remains the same. Okay, now let's try to move a bit further and find it on another location. Do we see the same thing happening across the board again? Right?
Yeah.
So this would be my angle of reflection at this location.
Because then the rest of the part that has collided already then collides and it reflects.
Yeah. So this part has already reflected back, or has already collided with the barrier, and the rest of the part still has to do that. So let's keep on watching this. Let's keep on visualizing it for better understanding. It will show you the same thing again and again. Right? And then again at this point. Okay, so he's going to mention the same thing that we've just done, right? But with different angles. So do we understand how the reflection takes place at a barrier within a ripple tank?
Yes.
Okay. Now this is a new barrier at a new location doing the same thing at the same time. I'm going to clear out this screen for you so that we can visualize it again. So at this location, if I had to draw normal, that would be perpendicular to the surface, which is of course going to make an angle of 90 degrees with the surface. This one would be my angle of incidence, and this one would be my angle of reflection. This concept that you measure the angle with the surface is wrong. You will not measure the angles with the surface, you will measure it with the normal. That is why we are drawing the normal. Okay, and of course normal makes an angle of 90 degrees with the surface. I've just drawn it over here so that I have some space to draw these at this point. Otherwise it will be on the same side. Is this clear now? Yes?
Yeah.
Okay. A much steeper angle and see what happens. Okay, so again, if I had to locate my normal, that would be at this point where it strikes the ground. If I had to locate my angle of incidence, then that would be this one. Angle of reflection would be this one. So this is the wave that still has to collide with the wall, and this is the part of the wave that has already collided with the wall. Okay, and we can see that for a reflection, specifically for reflection, the angle of incidence is supposed to be equal to the angle of reflection. This is a rule, or you can say the principle of reflection, that both angles are equal.
Mm-hmm.
Is that acceptable? Yes?
Yeah, yeah. Mm.
Okay, all right. It's the same reflection video, right? Just one more aspect will be added in this location. Do you see how many wavefronts there are? And every single one of them is being reflected in the same way that we did before.
Mm-hmm.
So every wavefront will have its own normal, will have its own angle of incidence, will have its own angle of reflection. Do we understand this point? Can we visualize it?
Yes. Mm.
Okay. Right?
Mm-hmm. Yeah.
Okay.